we're moving to the field of laser trapping and cooling. We all learned that light has a momentum, but can it be used to manipulate objects? Arthur Ashkin will talk to us about the early days of laser trapping and manipulation of particles by lasers.
I consider it a pretty great honor to be invited to speak at this symposium. Jim was my friend and he was a colleague. I was asked to speak about what I did with Jim Gordon in the early days of laser trapping. And I consider this work to be the most interesting and important work of my whole career. Its origin, however, goes back a long ways, 70 years to the start of World War II in 1941. Not many people were around there from out in the audience. I was 20 years old at that time and a sophomore physics major at Columbia College. I was a good student and they offered me a job with a deferment to work at the recently formed Columbia Radiation Lab. I was their first technician. My draft board in Brooklyn, however, saw things a little bit differently, and I was promptly drafted. Well, I ended up serving a total of about 6 years in the Army at the Radiation Lab until 1947. At the lab, there was a guy, Sid Millman. You Bell Labs people know him. He was the inventor of the Rising Sun magnetron. He was my mentor. And he really taught me how to be an experimental physicist. Millman had me build in 1944 a high-power X-band magnetron, 3 centimeters. It had a record power output of about 1 megawatt, okay? I built it, but it was never used in the war. But I did have a little fun with the magnetron. I did an experiment demonstrating light pressure. Now, this was never published, but it did alert me to the subject. After the war, I graduated from Columbia College, and I got a PhD in nuclear physics in 1952 from Cornell, okay? Now, with Millman's help, I got a job at Bell Labs in a microwave department, and meanwhile, as we've all heard here previously, Jim was finishing up his famous experiment with Professor Towns, and he also took a job at the same group. Now, our careers at Bell Labs were initially quite different. Mine started badly. My department head asked me to demonstrate a theory he had about canceling noise on electron beams, this is, okay? We were a microwave tube group, and this was a physical impossibility, and I, of course, failed. So after a year, I ended up almost fired and no raise, okay? Fortunately, my department had saved me, and eventually I found my own way at Bell Labs. I worked on a lot of things in the 50s. I studied electron beams and magnetic fields and electron beam parametric amplifiers. We heard about Louis Zell. Well, I did the experiments that Louis Zell used in his book, his well-known book. But Jim's career was very much more focused. He concentrated on masons and later on lasers, and he was quickly promoted to be a department head, and he assembled a very impressive group that did much of the early work, as you've just heard, and more, okay? And in 1963, finally, after 10 years, I was promoted to department head, and I had mostly technicians and shop people in my group. So this gave me a rather late start on laser work. Well, I actually got my start by attending an Optical Society meeting in 1969. Okay? I heard a talk on something called runners and bouncers. You probably never heard of that, but there were strange small particles that people would see inside of cavity resonators that would go zipping back and forth, running and bouncing. Now, it was speculated that this might be radiation pressure. It turned out it wasn't. It turned out to be actually a radiometric effect, just plain old heat. But this reminded me of my magnetron days, and I asked myself, could I take a laser and actually make a push and observe light pressure on small transparent particles in water? That would be, in water, there would be very little heat. Maybe we'd see it. Well, the experiment worked almost immediately. The little spheres zipped around through the water, and then I noticed some strange behavior. Okay, I'm an experimentalist. It happened. Particles were being pulled into the high-intensity region of the laser beam as they were pushed along, and when they hit the output face, they were impaled on the output face. They stayed there. Well, it occurred to me that I could make an optical trap if I took away the wall and put a second beam in the opposite direction. Let's see if this slide shows that. Yeah. The geometry is shown on the right. If you move that little sphere in any direction, there's a restoring force, so it's stable. Now, the optics is very simple. They would show on the left a Gaussian beam and a couple of rays going through the sphere. There's more power on the A side than the B side, and the forces are in the direction of the momentum change, and they have components driving it forward and pulling it in, okay? So they're very simple optics, first trap. But that was a very breakthrough moment for me, and I think for the history of optical trapping. Okay? Now, I even speculated, I decided I was going to write this up. I speculated that maybe you could even trap atoms. Atoms are just little spheres, dielectric, and maybe even biological particles. But they'd probably be all burned to pieces. But anyway, I wrote my results for phys rev letters. And at Bell Labs at that time, if you wrote a paper going to phys rev letters, they had an internal review system and had to go to the theoretical physics department to check out its, whether it was destroying the reputation of the laboratory. Well, the review came back and it was rejected. Rejected on 4 grounds. Number 1, no new physics, okay? Number 2, let's see, yeah. Oh, number 2, it's not even wrong. That's a form of the Pauli insult. When Pauli found something that was particularly trivial, he used that insult, okay? And on number 3, it said it could be published somewhere. And number 4, but not in phys rev letters, okay? So I was very upset, but our director, Rudy Comfer, you may not know him, he's the inventor of the traveling wave tube. People call it traveling wave masers nowadays. But anyway, he was a very mild-mannered man, and when he heard of the rejection, he simply said, damn it, send it in. So we sent it in, and it was accepted. Okay? And it turns out that is one of the most, I've been told this, I suppose it's true, that it's one of the citation classics in the physical society. Okay? But I followed up with a number of experiments and proposals using trapping. I suggested devices like atomic beam velocity analyzers and atomic beam isotope separators. All these things work. An important paper, however, was a Henshin shallow paper. That was proposed that you could use atom damping, using atom damping from use the Doppler shift and radiation pressure. That's a very familiar device, but there was only one reference in the paper, and that was to me. They never even mentioned trapping atoms, okay? So they weren't that all interested. Now, most experiments in the early 70s and 80s were on micron-sized dielectric spheres, however. Well, we studied levitation against gravity. He's trying to beam up, and let's see if there's a picture there. Yeah, there you see a beam holding a sphere up against gravity. Okay, that was the first levitation experiment. I submitted this to applied physics labs, came back rejected. Why? It's been done before, okay? But the guy could never come up with the exact reference, so the editor accepted the paper. All right? Now, with this kind of a thing, I show you there that if you look at the sphere and sense its position, you could make what I called a force. Well, what I'm saying is that we use a sensor to feedback stabilize the particle in one position. If you apply a force and the force changes, well, the feedback system changes the input power so that the input power is a measure of the force. So that's a force measuring instrument. And we used it to make a very precise optical Millikan oil drop experiment. Okay, now maybe we'll look at the next. Yeah, this shows how the particle is staying fixed, and all those little steps represent single electron events that are taking place over time as you shine in some UV light. There's tremendous resolution there, and you notice there's no third electrons. So that was a question. In the early days, people thought that the charge on the electron was not even fixed. There's a guy, Herrenhoft, who he's the inventor of radiometric effects. But so I think this was an important experiment. Let's see. What do I want to say now? Oh, we did a lot of experiments of this sort. Whoops, let's go on. Here, I thought, well, let's look at the wavelength dependence of the force. You see how the power levitation varies as a wavelength. You had a dye laser, we swept it across the whole over a wavelength region, and looking at the spectrum A, it looks pretty garbagey. I thought, well, maybe the apparatus is not working, but if you put another particle in and compares spectrum B to spectrum A, you notice it's identical, except it's shifted. And it's shifted because it has a different size. These are resonances. So these are surface wave resonances. And with these kind of measurements, you can measure the size of a sphere, the diameter, to 1 part in 10 to the 8th, or even higher. And you can measure the index of refraction to that kind of accuracy. So Millikan's measurement was never used for the charge of the electron. In fact, he got it wrong. But I think this has the potential of being a very important experiment. Now, in 1978, time is moving on. I invented the optical tweezer trap for macroscopic particles. Let's see if we see something. Let's see. I just want to show you this very quickly. What? Oh, okay. Okay. Well, I can look at this side and see it too. Well, okay, the audience is here and there. Come on, don't hide. All right, look at these pictures. These are a comparison between theoretical and experimental light scattering spectra. The top one is theoretical, calculated from me theory, using computers. They didn't have computers in the old days, and 4 spheres, and this is optical wavelength. And look at the comparison between the top and the bottom, almost perfect. I think this is the most precise light scattering experiment ever done, and if you want to think of it that way, I think it confirms Maxwell's theory. Right? Okay. But now let me tell you that Jim Gordon was always a supporter of light force experiments. I spoke to him a lot in the early days, and eventually we became collaborators. In 1980, Gordon and Ashkin showed that one could indeed nominally trap a nominally stable atom optically. Now, I'm a little incoherent. I'm saying we showed that we could use, with 2 beams, you could trap an atom. One trap, you would make a very deep, tune off resonance, make a very deep trap, and with the second beam, you could optimally cool it. So with that combination, you could make traps. Okay? Well, at this point, there was actually no rigorous theory of the quantum theory of trapping and cooling. A lot of it was just hand-waving, like I showed you. And Jim decided to develop a theory on his own. So he had a number of new features that showed up in this theory, and when he wrote up a paper, and I looked at it, showed it to me, he put my name on it. So I told him, I don't belong on this paper. I can't understand the mathematics. So he said, well, you explain what the problems were, and I solved it. So we collaborated, and he insisted that the name stay on it, and that turned out to be probably the most famous theory paper in the whole field of optical trapping, okay? So I'm very grateful for that. Now, in 1963, a guy called Bill Phillips at the National Bureau of Standards, he was working with a guy called Metcalf, and he was using light pressure to stop atomic beams. All right, a beam comes here, and you shine light that way, the beam comes to complete rest. Well, it still has thermal noise and had a temperature of about 1 degree, okay, 1 degree Kelvin. Not 3 degrees, 1 degree, okay? Well, they were, at the Bureau, they were very proud of that, and they held a conference in which Jim and I and John Bjorkholm, we were invited, and Bill Phillips gave his presentation, and at the end of the presentation he said, and now we're going to, next experiment is to trap atoms with light using cooled atoms. And when we got home, I told Jim, you know, he specifically mentioned the trap. He said the trap has recently been published in optics letters. Well, I told Jim that I had actually shown that that trap was leaky. There were directions where the atoms were not stable. The atoms would escape. And then I told him that I also suspected that there was an optical Earnshaw theorem in analogy with the optical Earnshaw theorem on electrons that said that maybe there was no such thing as a stable scattering force trap. Well, next day Jim comes back and says, well, I proved it, okay? So the question is, would we even publish it? Because we would alert Bill Phillips to the fact that his trap was leaky. And finally, we decided to publish it because our director, the boss, said that trapping is never going to work, and I'm not supporting it. So we published the theorem, alerted Bill Phillips, and we're sitting back waiting for him to get the first optical trap. Well, at that point, a guy showed up from Murray Hill by the name of Steve Chu. He was an atomic physicist. And he started talking to us. And I guess he got interested in trapping. But the boss told him, I won't mention his name, he said, Steve, he says, you can do anything, you can do anything you want, but don't work with a hard Ashkin on atom trapping, it's never going to work. Well, Steve had an intuition, and he joined us, he dropped his other plans, and we started a collaboration to do atom trapping. Well, Steve had the very good idea of first seeing if you could cool atoms using the Hessian shallow Doppler technique, and then after, if that succeeded, to proceed with trapping of atoms. Well, that was the way optical molasses, if you know that term, optical molasses was born. And with optical molasses, we made atom trapping, okay? But shortly after, well, we had a moment of fame there because the New York Times, on the Sunday Times, on the front page, mentioned about trapping of atoms with light. But at this point, the collaboration sort of disintegrated. People each went his own way. Chu took a job at Stanford, and he took his equipment with him. Leo Holberg, whom you may know, his postdoc, he went to go work at the Bureau of Standards. And Steve's technician, Alex Cable, he quit the labs, floor labs, which you may have heard, and he became a millionaire, okay? Well, that left me with Joe Dietrich, my technician at Bell Labs, and I stayed there ever since. But we had a bit of a breakthrough. Just by accident, we discovered that it's possible to trap bacteria, living things. We had a sample that we were trapping, and it was a good sample, so we said, let's keep it overnight, and we'll continue the experiment in the morning. Next day, we look in, turn on the light, and there's some kind of a wild scattering going on there. And I said to Joe, well, we got bugs. It turned out we did have bugs. The sample had become contaminated with bacteria, and the light beam was trapping the bacteria, okay? And they couldn't escape, so we had this wild scattering. Well, the next thing we did was to look at the trapping of living things with light. We visited all the ponds in the neighborhood, collecting paramecium, rotifers, all kinds of single-cell animals. And that was the beginning of the use of tweezers in biology, which has grown enormously, okay? There was a biophysicist by the name of Steve Block from who's now at Stanford. He began working on tweezers very early, and he did some of the most marvelous experiments. He trapped and measured the forces of molecular molecules which drive small particles inside of cells, okay? Oh, by inside of cells, the thing is that optical tweezers could actually work. This was a great surprise to me, could actually work inside of living cells if you used infrared light, because infrared light is less damaging. And we even did little operations moving around the guts of onion cells and things like that. But Steve went on to study other important molecules like DNA and RNA polymerase, and he did it at atomic resolution. He found that he could make traps so stable and so controlled that he could measure the genetic code at atomic resolution. Now that is a little late for. I mean, people have used force microscopy or to do the first, actually looking at atoms on surfaces, but I think that actually the tweezers is equally. Yeah, should I stop here? Well, okay, but all right. I will stop to say just a few things more. I think a lot of Nobel Prizes are going to appear in this field. We've had two, one for trapping of atoms and cooling. The other one was Bose-Einstein condensation. The final remark would be to cut through a lot of this is that tweezers has turned out to be a very important trap for studying Bose condensation. There was a time when they used magnetic traps, Mott traps. They were for 10 years that people thought that was the hottest things. But it turns out that tweezers is superior to the Mott trap in every respect. And there are some fabulous experiments that have gone on using superconductivity, superfluidity, atomic, you're seeing optical vortices, and so on. But you know, this is my last sentence. I used to talk with Jim, and I told him, you know, Jim, you're one of the only guys I ever knew who deserved 3 and maybe more for Nobel Prizes, but won none. So Jim just smiled, and then I remembered that little sign that you see there, that was shown here. He had this little sign in the office that said, there's no limit to what you can accomplish if you don't worry about who's getting all the credit, okay? So I think that Jim Gordon was a great friend, a great colleague, a great scientist, and especially a great human being. Okay?